Okay, so feedback in layman term, it's a process in which output is fed back to the input. So feedback is a process in which output is fed back to the input. Okay, so when you are feeding the output back to the input, you may feed 100% of the output or a part of the output. That depends on the requirement. All right. So when you feed the output, okay, when you feed the output to the input, you can feed in two different ways. Okay, you can feed the output in such a way that the output signal, okay, may be added with the input signal, okay, or the output signal may be subtracted from the input signal. Okay, so to understand that, what I have done is I have constructed a simple feedback mechanism block diagram. Okay, so here you can see the bidirectional signal flow, right? In the top half of the circuitry, the signal is flowing from left to right, right? So that is, the signal is starting from, say R, and then the signal becomes E, and then finally you get the signal which is C. Okay, so the signal is flowing from left to right in the top half. Excuse me. On the other hand, in the bottom half, the signal is flowing from right to left. So in a typical feedback system, you will have bidirectional signal flow. Okay, so in the top half we have an amplifier circuit, and in the bottom half we have a feedback network. Okay, so we have marked different signals here. Okay, signal R, signal E, signal C, and signal B. Okay, what are those signals? The left-bound signal, okay, the leftmost signal, I'm sorry, which is taken as R, which is nothing but our input signal, or sometimes it is also called as reference input. All right, and C is considered as the output signal or output of the system. All right, now we are feeding the output signal back to the input signal using a device called feedback system. Okay, so what we are doing over here is that we tap the output signal. Okay, we tap the output signal and we feed it back to the feedback signal, the feedback circuit. And this feedback circuit will give you a signal which is considered as B. So B is equal to feedback signal. Okay. Then in the beginning I said the manner in which the feedback signal is handled. You can have two types of feedback topologies. Either you can have positive feedback topology or you can have negative feedback topology. Okay. Let's say, for instance, if your feedback signal B is added with reference signal R, then you will get a kind of positive feedback. So positive feedback, what it does is it simply increases the signal strength. So the error signal E is nothing but the addition of reference signal and the feedback signal. Okay, so that's for a positive feedback system. On the other hand, for a negative feedback system, what we do is we subtract the feedback signal B from the reference input R. So the error signal E is nothing but the difference of R minus B. Okay, so I can give you an example what you mean by this positive feedback and what you mean by negative feedback, right? So before that, let me tell you one thing. This positive feedback is seldomly used in nature. Okay, the systems what we use in our day-to-day life, almost all systems belong to this negative feedback category. You can say that more than 99% systems are negative feedback types of system. Okay, in positive feedback, okay, we don't use many systems except for oscillator. Okay, so oscillator is a electronic circuit which works on the principle of positive feedback. Okay, That also I'll tell you why. See, you cannot use positive feedback in our day-to-day life simply because you look at the error signal. So error signal is the addition of reference and the feedback signal. So what is happening is the error signal is basically increasing in case of positive feedback. You don't want the error to increase, right? So if the error increases, then your system will not give you an expected behavior. Okay, that's the reason, it is not used in consumer electronics, etc., etc. Okay, so it is only used in oscillator. Now we need a device which is capable of reducing the error. So that is possible if we go for negative feedback topology. Okay, let me give you a simple example. Consider your automatic air conditioning system. Okay, let us say the reference input is 30 degrees Celsius. That means to say we want our room temperature, okay, to be there at 30 degrees Celsius. Okay, and let us say the actual room temperature is somewhere about 35 degrees Celsius. Okay, so we have set 30 degrees Celsius in the air conditioner, okay, by operating the remote control. So we set 30 degrees Celsius in the remote. Okay, so what will happen, the sensor or the thermistor which is there in the air conditioner, it will immediately senses the ambient temperature. Okay, let's say the ambient temperature at a given interval of time is 35 degrees Celsius. Okay, so what will happen is the feedback mechanism, okay, this feedback sensor, it basically senses the ambient temperature and feeds the signal back to the this is called as mixer, okay, or comparator. This is also called as comparator, which compares the two signals. So this feedback system senses the output and feeds back to the input. So what happens over here is that you get signal B as 35 degrees Celsius. Okay, due to which what happens is that for a positive feedback network, okay, the error becomes, E becomes 30 plus 35 is equal to 65 degrees Celsius. On the other hand, for a negative feedback system, the error becomes 30 minus 35 is equal to minus 5 degrees Celsius. Okay, you see the difference. Your first system gives 65 degrees Celsius as the error, and the second system gives minus 5 degrees Celsius as the error. Okay, now imagine if you go for a positive feedback system. So if you go for a positive feedback system, what happens is that this error signal becomes 65 degrees Celsius. Okay, and this error signal will prompt, or it will make the refrigerating system to increase the temperature to 65 degrees Celsius, because the refrigerator system is a brainless device. It just takes the input and gives the output. The input is 65 degrees Celsius, so it simply tries to increase the temperature to 65 degrees Celsius. Okay, so the whole objective is lost. The set objective was to keep the room temperature at 30 degrees Celsius, but due to the positive feedback mechanism, the room temperature has gone up to 65 degrees Celsius. So that's the reason you will not find positive feedback mechanism in our day-to-day life consumer electronic products. Okay, now let me go for the second type of feedback. Okay, if in case your air conditioning system had negative feedback, then what would have happened? If there was negative feedback, then the error signal, okay, error signal would have been minus 5 degrees Celsius. That means to say the refrigeration system, okay, which is there within the air conditioning system, tries to reduce the temperature by 5 degrees Celsius, due to which what will happen is the new temperature drops down to 30 degrees Celsius, and the output, okay, which is now at 30 degrees Celsius, is going to match with the input. So you can say that the objective is met. So this is how the feedback, topology works. Okay. Hope you understood the difference between positive and negative feedback. Okay. If yes, can I get quickly why in the chat box? Okay, fine, great, fine. So that's all. So that's the difference between positive and negative feedback. Okay. So features, let me talk about the features. The only good thing about positive feedback is that, it increases the output. It increases the output, which is, useful only for oscillator. It is useful only for oscillator. So in case of oscillator, we want our output to grow. So in order to, increase the output, we'll go for a positive feedback topology. Okay, that's the only one usefulness. Okay, and that is possible. That is possible due to very high overall gain. Okay, very high overall gain. Okay, so that's the feature of positive feedback. So positive feedback gives very high overall gain. On the other hand, in negative feedback, okay, only one drawback. Okay, only one drawback is that overall gain is less. Okay, overall gain is less. So except for this drawback, rest all you will find it as advantages. Okay, there are plenty of advantages. There are many advantages having a negative feedback system. Okay, the first advantage is bandwidth increases. Bandwidth increases. By increasing the bandwidth, what will happen? You will have a wider, space to operate the system, basically. Okay, bandwidth increases, then it, reduces noise. Reduces the noise. There are so many. Okay, it gives, more linear operation. Okay. Linear systems are very easy to handle, right? And it gives stability. Okay. Stability in the sense the system, behaves stable for any disturbances caused. Okay, so these are the major advantages, okay, of negative feedback system. Okay, only one disadvantage is that the overall gain is less. Except for this disadvantage, you have many advantages. Okay, whereas vice versa holds good for a positive feedback system. You have only one advantage, that is overall gain is pretty high. Except for one advantage, you have, several disadvantages. That is lower bandwidth, higher noise, and non-linear operation, unstable. So those are the disadvantages of positive feedback system. All right, fine. So that's about the first part, feedback concept. Okay, now let us look at the second part, which is the block diagram of feedback network. Okay, so let me write the second one. Block diagram of feedback network. Okay, fine. So let me draw the block diagram of feedback network. Okay. So the first block in the feedback network is the signal source, okay, followed by a comparator or mixer, then followed by the basic amplifier, okay, then followed by a sampling network. Okay. So these are the major 4 blocks that you are going to see in the forward path. Whereas in the backward path or in the reverse path, okay, you will find a feedback network. All right. Now let's start connecting the blocks. All right. So this is your source. So source signal is connected to the mixer, okay, or comparator, one and the same. And the comparator output is given to the basic amplifier. This is your basic amplifier. Let us say the gain of basic amplifier is A, all right. And the basic amplifier output is then given to a sampling network. Okay. And the output of the sampler, okay, is taken across the load. Okay. So V0 basically, you know, the output. Okay. Now, the sampling network basically what it does is it takes the part of the output. Okay, so this sampling network takes the part of the output and feeds back to the feedback network. So this is your feedback network. In short, let me write N bar W feedback network. So this feedback network will have a gain beta. Okay, remember, do not get confused with the current gain. So beta in feedback amplifiers refers to the feedback gain. Okay. Now this output of this feedback, okay, is then given to the comparator or the mixer. Okay, or the mixer. So this is the basic block diagram of, you know, a typical feedback arrangement. Okay. So let us mark different signal. Let us define source signal as VS. Okay. And the feedback signal as VF. Okay, so this is our source signal, and VF is our feedback signal, and VS and VF, you know, they'll be compared in the mixer, and we'll get the input signal VI. So this input signal VI is given to the amplifier input, and this amplifier gives an output V0. Okay, and a part of output V0 is fed back to the comparator through the feedback network beta. All right. Now remember one thing: this beta, okay, beta value ranges from 0 to 1. Okay, 0 to 1. That means to say, if beta is equal to 0, okay, no feedback. On the other hand, if beta is equal to 1, then 100% of the output is fed back. Okay. On the other hand, if you keep a fraction, let's say beta is equal to 0.5, that means to say 50% of the output is fed back. So that means to say, this is your V0, right? Because through the sampling network, you will collect the V0, okay, and you will feed this V0 to the mixer using the feedback gain beta. So expression for VF is basically beta into V0, okay. So now you can appreciate, right? So VF is equal to beta into V0, okay. If beta is equal to 0, VF is equal to 0. That means to say no feedback. No feedback signal means no feedback. On the other hand, if beta is equal to 1, then VF is equal to V0. So feedback signal is equal to output voltage. So that is nothing but 100% of the output is being fed back to the comparator. On the other hand, if beta is equal to 0.5, how much you will get VF as? VF you will get it as 0.5 times the output, or 50% of the output. So 50% of the output is fed. So that is the understanding of the term beta. All right. On the other hand, this amplifier gain A, okay, it can vary from 1 to finite number. Okay, 1 to finite number. Okay, 1 for emitter follower, where gain is 1 unity. Emitter follower. And the finite number refers to either common emitter stage or a common base configuration amplifier. Okay. Now you remember one thing: this basic amplifier need not be the voltage amplifier. It can be the current amplifier or any other amplifier circuit. Okay. Let me get into that. So first, let me talk about the first block, which is the leftmost block, which is the source signal. Okay, source signal. Now, in your feedback system, there can be two sources. It can be a voltage source, okay, or it can be a current source. Current source. Okay. The voltage source, if at all is given, then you would represent voltage source something like this. Okay. The series resistance of the source and the potential of the source. On the other hand, if at all current source is given, then the current source representation will be done something like this. Okay. Okay. So very simple. You can have two types of signals, either voltage source or you can have a current source. Okay. Next we have the comparator block. Okay. What do you mean by a comparator or a mixer? Okay, bar mixer. Okay, mixer or comparator. Okay, basically it's a device which compares two or more signals and gives one output. Okay, it can compare two or more signals and it can give one output. So the basic example for comparator going to be an op-amp. Okay, op-amp. So op-amp will have two terminals, two input terminals, right? Non-inverting input and inverting input. So what you can do is, probably the source signal can be given to, let's say, non-inverting input, and the feedback signal can be given to the inverting input. Okay, and the op-amp gives the output V. Okay, output V0. So it holds good for, let's say, IS, IF, okay, or I0. Even you can give the current signals, provided you derive the current signals using some circuit. Okay, so that's the meaning of your comparator block. Okay, meant for comparing the signals. It compares the signals and gives an output. Okay, now okay, Yeah. So output, okay, we'll not take it as V naught, we'll take it as Vi, because okay, this is II. Okay. So this Vi is basically difference of Vs minus Vf for negative feedback, because in case of negative feedback, you had seen that the signals are subtracted from each other, right? On the other hand, for a positive feedback, the source signal is added with the feedback signal. Source signal is added with the feedback signal. Okay. So that's the meaning of the comparator block. Okay. Now, in electrical as well as electronic circuits, you know that signals can be of two types. You can have either voltage signal, or you can have a current signal. Okay. You can have either voltage signal or current signal. Now, if in case you want to handle, or if you want to compare the voltage signals, okay, then the mixer what you are going to use, okay, or the comparator what you are going to use is series. The comparator what you are going to use is a series type. On the other hand, if at all you want to compare the current signals, then the comparator what you are going to use going to be a shunt type, which is called as shunt mixing. Okay. So the electrical diagram of series mixer is as shown. Let's say this is RS, okay, and let's say this is Vs, the source signal, okay. Now, in case of series mixing, what is happening is you're going to mix the source signal Vs with the feedback signal Vf, right? So something of this kind you will find. Okay. This is beta, the feedback element. Okay. So this feedback element gets V naught as the input, and it gives Vf as the output. So this Vf is then added with Vs, okay, to get the overall input Vi. Vi. So this Vi is then connected to the amplifier. Yeah. Okay. So this is the concept of the series mixing. Okay. This is the concept of series mixing. On the other hand, in case of shunt mixing, okay, you will have the current source. So basically it follows parallel circuit topology. So this is your current source, IS, okay, in parallel with the source resistance, RS. This is then connected across the amplifier block, A. Now, so this is about the source signal. How are you going to connect the feedback? So feedback is connected something like this. This is your feedback block with the gain beta. Okay. So your current mixing basically follows Parallel connection. Parallel connection. All right. So this is your input current, II, and this is your feedback current, IF. So this is the connection diagram of shunt mixer. Okay, so you have two mixers, series mixer and shunt mixer. Series mixer is used to handle voltage signals and shunt mixer is used to handle current signals. Okay, so that's your second block. The third block is the basic amplifier. Okay, basic amplifier. Let me show the block diagram. So source signal is done. We also spoke about mixer, and now we are considering the basic amplifier. Okay. Now, your amplifier is a two-terminal device. It will have input port and it will have output port. Okay. So let's say Xi is the input and X0 is the output. The gain of the amplifier, okay, is defined as output signal to the input signal, that is X0 by Xi. Okay. Now, X0 and Xi are the output and the input signals respectively. Now, depending upon the type of amplifier what you choose, you know, the X0 and Xi can be current signals or can be voltage signals, or it can be the combination of two. Okay, so accordingly, the amplifiers are categorized into four types. The first type of basic amplifier is the one which has X0 as well as Xi as the voltage signals. For example, let's say output signal is voltage signal and input signal is also voltage signal. Okay. And then the gain, whatever you get, is defined as the voltage gain, AV. Okay, so this is defined as voltage amplifier. Okay, which gives voltage gain. Similarly, you can also have, a gain which is derived by taking out the current signals only. So let's say your output signal is output current, and let's say your input is input current. So basically you are dividing output current with the input current. Hence, you will get a gain which is called as current gain, and the corresponding amplifier is called as current amplifier. Okay. Now comes the crazy part. Third type. You can also, take out the gain by taking X0 as V0 and Xi as Ia. So basically it is voltage to current ratio. Hence, the corresponding amplifier is called as trans resistance amplifier, because the gain is resistance basically. Trans resistance amplifier. So trans resistance amplifier is taken as AM, okay, or sometimes it is also taken as RM, because resistance symbol is R, right? Okay. And then we have the final type in which gain A can be found by taking out the ratio, something like take output signal as current and the input signal as voltage. So what do you get? I0 by Vi. So this is called as trans conductance amplifier. So trans conductance amplifier, okay, sometimes it is taken as G, okay, because the symbol of trans conductance is G. So it is G or GM, doesn't matter. Okay, the book says GM, so I'm taking GM, doesn't matter. Okay, so these are the four types of basic amplifier. So remember one thing, in feedback amplifiers, okay, the amplifier block A need not be a voltage gain. It can be current gain, it can be trans resistance, or it can be trans conductance. All right, fine. So we are done with the basic amplifier block. And finally, we have the sampling network. Sampling network. Okay. So in the beginning, I have told, right, what is the purpose of a sampler? So sampler basically helps in tapping out the output signal. Okay. Now you are, well versed with the signals. The signal can be a current signal, or signal can be a voltage signal. So if at all you want to tap a voltage signal, then what you need is a voltage sampler. All right. On the other hand, if at all you want to tap or want to feed current signal, then you need to go for a current sampler. Okay. Okay. Now, why do you need current sampler? Because in case of current amplifier, the output signal is the current signal. So you need to tap the current signal. Okay. So accordingly, you will have two types of sampling networks: voltage sampler and current sampler. Okay. First, let us look at the voltage sampler. How exactly you will be able to, tap the voltage signal as well as the current signal. Okay. So let's say this is our amplifier block. And let's say this is our feedback block, beta. Okay. So in case of voltage sampling, okay, let's say this is resistance RL, which is the load. So voltage is tapped by connecting the wires across the load resistor. Right. So what we have done is we have connected two wires across the load. See, one wire is connected to this end of the resistor, and the other wire is connected to this end of the resistor. So by doing which, what you can do is you can tap the voltage. Okay, you can tap the voltage. So this is called as voltage sampling. In case of current sampling, the other way around. Here you are basically constructing a parallel arrangement, right? So in case of current sampling, you need to have a series arrangement. That's all. Okay. So logically, you can remember these circuits. Say this is EA and say this is beta. Okay. So let's say your load. Okay. This is let's say your load. So this is your output current, let's say I0. Okay. So how are you going to tap this current I0 such that this current I0 flows to the feedback network as well? It flows to feedback network provided you give a kind of series connection. So this I0 will flow through the feedback network as well. So this type of arrangement is called as the current sampler. Okay, so there you are, two types of sampling network: voltage sampler and current sampler. Okay, done. Now the final element, which is the feedback element. So feedback network. Okay, so this feedback network, okay, is constructed mostly using passive elements. Passive elements such as resistors or capacitors. Okay, passive elements. And inductors also. Okay, and the gain of the feedback network. Okay, what is gain? Gain is nothing but output signal to the input signal. Input signal. Okay, so gain of feedback network. Let's say this is your feedback network. Okay, which gets some input as x0, okay, and it gives output as some xf, okay. So the gain is nothing but the output signal, which is x0, sorry, the input signal, sorry. Okay. The output signal, what is the output of feedback block? This is the output of feedback block, that is xf. And what is the input to the feedback block? The input is coming from the amplifier output, so x0. So xf by x0 is the gain of the feedback network, okay. So that's your feedback network, okay. About feedback network, we are not going to study in detail, because about feedback network, we are going to study in depth in module 4 in oscillators chapter, okay. So that's your block diagram of feedback network, okay. So we are done with block diagram on as well. So finally, let us take up an expression for transfer gain, okay. Let's come down. The third part is expression for transfer gain. Okay, all right. So quickly, let me construct the block diagram. So first, let me draw the block diagram. Okay, block diagram. Say you have two blocks, amplifier block and a feedback block. Okay, so let's say the amplifier gain is A and the feedback network gain is beta, okay. And let us also construct a comparator here. So this comparator gets an input XS, which is called as the source signal, okay. And this comparator is being connected with the feedback signal, which is coming from the feedback network. So this is your feedback signal XF, okay. And let us consider a negative feedback topology. That means to say this arrow is connected to the negative part of the mixer, and this is the positive part of the mixer, okay. The output of the mixer is then connected to the amplifier network, okay. And the output of the amplifier is taken as V0. And let us also feed the output to the feedback network, okay. Feedback network, okay. So you can clearly observe that the feedback block receives an input which is equal to V0. Sorry, let me not use voltage, okay, because in general it can be anything, right? So let me take this as x0. This is also x0 because the same output you're feeding back to the feedback network, right? And output of the feedback block, let's take it as xf, okay, fine. Then let us define the gain of amplifier block. So this is your amplifier and this is your feedback network. So gain of amplifier, okay, we shall consider it as A. So A is equal to, what is the gain? Output signal to the input signal. So for amplifier, output is x0 and the input is xi. So let's take this as xi, okay. Take it as equation 1. And let us also define overall gain. So while defining overall gain, let us take the overall gain of the amplifier as AF. So AF is defined as the output signal to the source signal. Okay, let's take it as equation 2. Okay, amplifier gain is output signal divided by xi, and the overall gain AF is the output signal x0 divided by the source signal xs. All right, so that's your equation 2. So from equation 2, you can write the output signal x0 as the, this is from equation 1. You can write output signal x0 is equal to amplifier gain A into xi. And xi is equal to, okay, what is xi? Xi is equal to difference of source signal and the feedback signal, because source signal is connected to plus part of the mixer and feedback signal is connected to minus part of the mixer. So your input signal xi is basically source signal minus the feedback signal. Okay, let's take it as equation 4. Okay, then also let us define the feedback gain beta. Okay, feedback gain beta. So what is feedback gain? So gain is output signal to the input signal. So output signal is xf and the input signal is x0. Okay, so output signal is xf and the input signal is x0. Okay, that implies your feedback signal xf is equal to beta times x0. Okay, so let's take this expression as 5. Now what you can do, you can start substituting. So substitute equation 4 in equation 5. Okay, sorry, equation 4 in equation 3, because equation 3 is xi, right? So x0 is equal to A into xi. In place of xi, we have xs minus xf. Okay, say this is equation 6. Now, in place of xf, you can substitute equation 5. So you can write substitute equation 5 in equation 6. So x0 is equal to A into xs minus xf. What is xf? Beta times x0. Okay, or you open up the brackets. X0 is equal to A into xs minus A beta into x0. So let us collect the like terms together. So x0 plus A beta times x0 is equal to A times xs. Okay, or keep x0 outside the bracket, so you would get 1 plus A beta, okay, is equal to A into xs, or you take out the ratio x0 by xs. Okay, what did we take? X0 by xf ratio, xs ratio as AF. So AF is equal to A divided by 1 plus A beta. Okay, so this is the expression for the feedback gain. Okay, that is the overall feedback, where A is equal to amplifier gain and beta is equal to feedback factor or feedback gain. Feedback gain, sometimes it is also called as feedback factor. Feedback factor. Okay, so remember this particular equation. Okay, let's say equation 7. Okay, so equation 7 gives overall gain AF for a negative feedback system. For a negative feedback system. Okay, for a positive feedback system, for a positive feedback system, you would have got the overall gain AF as A divided by 1 minus A beta. Okay, so this is the difference between positive feedback and negative feedback. So for positive feedback, you will have negative sign in the denominator, and for negative feedback, you will have a positive sign. So what I will do, let me write plus or minus, okay, here. So plus for negative feedback, and minus sign is for positive feedback. Okay, so that's the derivation. Okay, very important derivation for, you know, short notes they can ask. Okay, so all right, so that's it for the day. Okay, so just to quickly summarize, what we did today was we defined the feedback concept. We spoke about types of feedbacks, positive and negative feedback. So in case of positive feedback, the feedback signal is added with the source signal. On the other hand, for a negative feedback, the feedback signal is subtracted from the source signal. Okay, and also we looked at the features of positive and negative feedback. So positive feedback increases the gain. Okay, on the other hand, negative feedback decreases the gain. But the negative feedback system is having many advantages, such as it increases the stability, it increases the bandwidth, reduces the noise, and improves the linear behavior of the circuit, etc., etc. All right, and then we looked at the block diagram of feedback network. Okay, so in the block diagram we explained all the parts, okay, starting from source signal to the feedback block, and finally we derived an expression for transfer gain. Okay, so here in the bracket I've written voltage gain because this transfer gain can be anything. It can be voltage gain, current gain, and the resistance ratio, or the, you know, conductance. Okay, so that is what we did in today's class. All right, so I'll stop my discussion here. So in the next class, let us take up the feedback connections. All right, so if you have not given the attendance, please do give the attendance. If you have any doubts, you can ask me.